as you can see, the title of my talk is Making Decisions About Making Decisions About Making Decisions. And Alex has kind of pointed you already in the direction of things that I would like to talk about. So it's kind of actually a nice segue from Desmond's talk, thinking about things such as parameterizing musical events. And I'm trying to think maybe going the next level up and parameterizing your parameters, or even moving further out and using more abstract models to control these kind of musical phenomena or events, or very low level controls. So I've had a bit stolen from me. You can see here I'm not from here, I'm from Perth. I came here in 2017 to start a PhD. I am still a composer. I used to play viola more so. I had the kind of traditional orchestral training. But now I don't play as such. I just stare at a laptop screen for quite long periods of time. So my main interest is in technology, machine aesthetics, to an extent automation, but not in the sense of Alexa making my life easy, but handing off processes, musical thought, encoding ideas in the machine. So I thought I would give some context to something that happened before this piece, which was a piece or a patch or kind of just like something that I did, which I named Biomimicry, which was a max patch, which takes in sound, performs analysis on it, makes some sort of spectral distinction about grains of those sound, and recalls the grains back according to a live input. So it's kind of like based on the traditional, it's not like 40 years old or anything, it's quite new, but the Kata RT or mosaicing kind of process where you chunk up your sound, analyze it and recall it using some sort of model. I don't think there's enough time to play any sound, but this was kind of like my first foray into really handing off some sort of control to the computer. And mainly my job was kind of to design the system, incorporate some behaviors into that system, and then work with a performer to I guess, cull certain behaviors out or shape the response of the system in a way that I found satisfying to me, from quite like a noisy or I suppose erratic computer behavior that happened without any sort of treatment of what I'd done initially. So there's kind of this like process of me, I've made this system, I don't really know if it works that well, let's play with it. Oh, okay, it does this thing, no, I don't like that. How can I remove that? I'm not going to directly take out, all the high frequencies because this scratchy sound is happening. Maybe if there's a grain that is thought to be, have lots of high frequencies in it, let's make that probabilistically less likely to occur in a performance setting or something like that. So working at kind of an abstract level and handing off a lot of control to the real time with the machine. So the piece, where's my mouse gone? Oh yeah, and there's a nice little photo. This is a vocalist called Sage, back from Perth, and she did a live performance with it, which was somewhat successful. It definitely turned on and worked. It didn't blow up. Some things didn't happen that we would have liked to have happened, but and you can see it's just sitting off to the side, quite hidden from the audience. So it was quite an interesting experience, having people come up to me afterwards and be like, "Oh, what were you doing with the electronics? What was happening?" It's like I didn't do anything. I just did it all like a couple of weeks ago and then turned this system on now, and what you're hearing is its sort of encoded behaviors and the system. So the thing that I more specifically want to talk to you about today is this piece, or again this kind of blurry nomenclature comes up. Is it a piece, a patch, a system? This is the thing that I want to show you today, which was, well, I'll go from the start and sort of build you up to what's actually going on inside of it. It was mainly sort of instigated by me coming across this emulation of what's called forces, or the forces synthesizer or algorithm, which is from Chiat Lombard or Peter Blas's work. So let's have a quick look at I'll put my browser on that side. So this is a guide from his website on how to build one. So it's very, very in-depth. There's quite a lot of info here on how to solder it, what to use, what PCB components, blah, 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 all that kind of stuff. I came across the sound of the synth first, and then I went looking for an emulation for it. And there's actually this great website, part of the website here, which some people might be familiar with, but it's a philosophical paper. So you can see he's put scrawlings of things that rhyme with forces. My favorite is the special cuck, which comes in later. Yeah, here. It's quite interesting. I mean, it's quite an abstract and sort of artistic, philosophical system design here. But it actually gives a little bit of info about how it works, which is, well, yeah, here he gives some quite overt clues. So you can see that we've got the forces, they bounce off each other, their absolute boundaries are set by voltage dividers. We have two groups of forces, and then there's some names. And this is not scientific, well, it's semi-scientific at least. But I thought, this is cool, this is interesting, this is engaging me. So I went and looked for an emulation, which led me over here. Which is from, well, the post was by Rodrigo, but I know that Pierre was involved in making the emulation as well. And it's like a really nice thread.
More importantly, Peter himself explained a bit of these drawings to us.
Oh, okay. So you had some insider knowledge then.
Some sort. As much as this guy can make 2 sentences in a row like this.
Yeah.
Video link.
Yes, yeah. Yeah, it speaks in riddles, I think. But yeah, so what I came out with was a patch that made some sound and had an interface to it. So there's, it's quite complicated. There's like a lot of parameters. It's noisy. It doesn't operate in a linear fashion. It's chaotic. I'm going to get that off the screen because it's kind of distracting. But so I came to this bit of code and this sound making object from two perspectives. I was thinking, yep, this sounds great. How might I exploit the kind of corners of this synth, the edge cases, the parameters inside of this world, where I can sort of milk varied and interesting compositional ideas, but also because it's so complicated, how might I use the machine to discover the edge cases? How might I get it to navigate them for me in a way that produces something that I am engaged with or satisfied with creatively? So, I'll just, yeah. The context of finding this synth, I was writing the piece for tonight, or writing at least some form of it that hasn't made it entirely into tonight. Where I was doing a lot with structural composites and building out sections from smaller kernels of information. And I was getting very frustrated with the kind of numerical game of building small structures and trying to proliferate them into larger ones. So I was thinking, well, how can I deal with time time and structure from a very abstract and distant perspective? How can I zoom out on the piece and think very generally rather than trying to do sort of micro composition? And as well as thinking, how might I do this? How can I get away from working so surgically with a very, very simple compositional language, which is supported by a complex programmatic language? I was also frustrated by this kind of friction that I was having between myself and the computer, the sort of unmanageability of the technical side of things. So number one, which I'm sure everyone's come across, is taking too long to make a sound that you're happy with. So playing with parameters and moving them, I'm not interested in doing that too much. As well as trying to track these two strands of thought, like, I'm building this technical thing and I'm trying to do a creative thing at the same time. As soon as you get kind of like a creative spark in one area, you have to forego the other one, and then you start losing track of these two things, and they start actually like losing touch with each other. So I wanted something that was quite dirty and quick, I suppose is the best way to put it. So some compositional sound things that I was aiming for. In the material, I wanted to make a space that was sort of, I've used the word self-relevant, which is kind of fraught right now, but something that was in a way focused and not just quite broad and random. So in this realm of alleviating my compositional decisions and encoding ideas, how can I still keep it quite concise without letting in too much, I suppose, noise or extraneous thought into the encoding process? How can I make it textually rich and diverse within quite a narrow, well, not a narrow space, but within the space that I have chosen to work in? So, not being too fixed by the technology or finding that I'm frustrated by the limitations of the technology in creating diversity, as well as a sort of flexibility. One thing that I think I was actively trying to work against was creating flat dynamics. So trying to create an expansive dynamic palette for the amplitude. And time. I kind of spoke about this, but yeah, I didn't want to be manually fixing sections with this piece. I didn't want to kind of be going through and thinking, well, what comes next? I wanted to zoom out on that process and move away from composing with composites and working towards a more abstract composition, as well as I didn't want to work on the microstructure so much that with the hope that it might lead to an intelligible macrostructure. I wanted to forego that kind of utopian thought that the process might give rise to something. As well, is that on? Yeah. So this idea of maybe encoding some sort of intentionality into the machine as well. And this idea of intentionality is not as easy to describe as like material or time or form or things like that. But I think it's quite easy to hear what intentionality might sound like when you hear a piece of music. It's quite easy to play like a random object into a MIDI synth and be like, yeah, that feels like it has no direction or no kind of focus. And I wanted to do whatever the opposite of that was and to have this kind of focused intelligibility or perhaps at least some sort of direction. So the synth itself that I put together, well, hacked together from other people's work, was they kind of explained it. It contains 4 of these forces. They're fed back into each other. And each force has 6 parameters which control the upper limits of the oscillations that occur within the algorithm, as well as the gain of the feedback that they receive from other forces. Because all up this is 24 parameters, which is a lot to be dealing with, especially when they're so chaotic. I did this kind of cheap way of just mapping out a single knob into 24 parameters, which it's easier to just show than to explain. Is that going to come up? Just opening a pack. So, is that incredibly tiny? Should I go like that? So, here is my knob or single input. And all I'm doing is scanning, it's come up on here. Yeah, all I'm doing is scanning through a noise map. And what this means is I can create sort of a bounded, limited single input and map it to some sort of noisy or multi-dimensional space. And then what this does is it's going into the slider translation, which does some sort of message formatting, and then into the actual synth itself. And for some reason I can't, it's up here. Yeah, so just goes into there and it's passed. So you can see each one of these is a force with its 6 parameters and its feedback going between the different forces.
Can you open a force?
Yeah, this is where it gets spaghetti. Sorry. Pardon? It's not so bad. It'd be nice if it had color, maybe. But again, like a lot of this is me tidying up other people's work, not necessarily doing it all from scratch. Although there are some sort of creative changes that I made where I took out the smoothing that they did on parameter inputs and such. So this bit will make sense in a second when I explain it. So I had this. Oh, let's actually hear it. That would probably give some good context. I'll just keep it there. So. So you can see the parameter space is large, and one parameter can actually do quite a fair bit to the activity. This isn't so much. Let's try and find one that will. But the kind of interesting thing as well is it's not really humanly understandable because as soon as you adjust one parameter, the implication of another one will change. So, I mean, if I do that, then that one, then I go back to that one and put it here and then change this. Like it's way too hard to try and work out what's doing what. So I thought that's actually a great problem for me to try and solve by handing off a lot of the decision making and traversal of this parameter space to the machine. So I was digging around. Oh, let's get rid of the audio. Or should we just do the whole thing with some sort of white noise? Yeah, so I came across this algorithm. I'm not really sure how. It was the internet or something. Just something happened. And I came across simulated annealing, which is this algorithm for finding. It's an optimization function, but it allows you to find minima or maxima in a parameter or just a data set or a space. But it's great because it's cheap. It's pretty easy to run. It's kind of slow, but that's not too much of a problem. It's not slow enough to encumber this particular thing that I was trying to do. But we'll try and let's look at some. We'll start increasingly.
Optimize your lunch.
Yeah, that's where it gets interesting. So this is the temperature of the system dropping. It's trying to find the maxima of this data space. So you can see as the temperature drops, we hone in on the peak. Great. Now you all understand it. No, let's move on to the traveling. It gets a little bit more complicated. So we can see here it's trying to find the shortest distance to connect all the points. So it's kind of a classic problem that people like to show. This one's way cooler, but actually no, we'll go to the really good one. So this one's actually doesn't have much fun stuff to look at, but it's talking about how you might use this algorithm to optimize complicated kind of things. Although lunch might seem quite simple, the criteria which you impose on that process for decision making is complicated because you want this cuisine but not with sauce, and I want it to be hot but I want a side that's cold. You start adding up all these different kind of decisions, and the algorithm kind of just like chunks them all together and gives it one encoded value saying, yeah, this is like better than this one because more things are right in it. And you start to work towards finding reasonable solutions within that space. So this one is quite good, and actually I'll close it right now. No, I won't close it right now. I'll open it right now. Yeah, no. So this is quite a nice, let's do a cat, that seems adequate. All right. So the idea of the algorithm is that it's a mimicry of the actual process of annealing, where you heat something up quite high and then you cool it slowly over time. And the idea is that you have, in metal you have structures that are weak, but when you heat them up and let them cool, they reset to a strong structure. And the algorithm follows a very similar process. So you have a temperature coefficient, which starts quite high. Every iteration you drop that coefficient by a certain amount. And you make random moves within a space. So like with that example of finding the weather data, it moves through the space randomly. It attempts to find temperature values which are increasingly more to find the maximum. But sometimes you're going to make wrong decisions in that space. And what the temperature coefficient says is, well, when we're at a high temperature, let's allow some of those wrong decisions to actually be made. Unlike a traditional hill climbing algorithm, which just keeps going, trying to go higher and higher, this lets in bad things. And the idea is that instead of, let's say you have a data set which is like a little peak here, a little maximum, a local maximum, and then you have a global one, you can actually escape that smaller one to find the bigger one over a long period of time, which makes it good for problems exactly as I just explained. But this is cool. So this one unshreds an image. So if we have this image here and then we do some stuff to it. So the great thing about this algorithm is it's not perfect as well. And what I think you would usually do is run it a lot of times and then start averaging or taking the best of many iterations of the iterations. So you can see here there's like a current energy value, which is, I guess it's doing some sort of comparison. It knows what it's meant to look like and what it currently looks like. And you're trying to maximize the closeness of your output. But these two, it's very simple as well. There's only two kind of parameters that you need to adjust. So if we make it only 1 million parameters and like, I don't know, 50 for the starting temperature, let's shuffle it and then re-anneal it. I mean, it's like worse, but it's different.
Is it not judging it on like smoothness or the similarity or something?
Well, that's what I think it does. Is
it doesn't need to know what the image is. It just knows that the image.
It could just be doing like, oh, that these pixels in a certain area are like similar to the original image.
Like slicing on one dimension, so it must just be.
No, but surely it compares slices that are next to one another.
Yeah.
And tries to make them more continuous.
Well, yeah, which is why you get the grouping kind of structure going on.
Put in a noisy signal will it produce structure from that.
Well, yeah. It will try and find. I mean, it might. I guess you might, if you put in like jit.noise with like color, you might get some sort of like gradient or something like that. I don't know. I haven't actually tried, but that is the kind of thinking behind giving it, or like working in this really noisy synth space. You know, I hear noise, and that's quite a simple symbolic like affect to me. It's like, oh, it's noisy, oh, it's a little bit pitched. But to the computer, it's 24 parameters at 0.5, 0.432. You know, like it gets quite complicated for the computer, and it tries to make sense of that in a very, very different way. And that's what I was interested in, is how can I traverse the space, and how can I exploit this machine behavior to make sound. It's also, yeah, as you can see, it's quite convergent. If I were to, let's be silly, let's do that, and then give it a higher size. So it's going to anneal for much longer. The idea is that maybe you would reach a better result, but actually it kind of just always converges on quite a similar thing.
If you click on the link on the description, on another page, Unleash simulated annealing on a toy problem full of random colorful pixels.
Yeah, okay, let's do that.
Just for fun, while we're here.
Let's do some real-time presentation. All right. Yes, okay, is there a... Yeah, okay, this is exactly what you were talking about, I think. So, if we look at the OG...
You don't need to wait for the maths, it's done for you.
Yeah. Okay.
So yeah, it creates structure.
Yeah, it does. I guess it tries to put colors next to each other. Yeah, it kind of, I mean...
But this is 2D, and the cat picture was
2D as well.
Drawings.
Is what?
Yeah.
This is a 2D thing, and the cat picture is vertical lines, so if you do that...
Yeah, I think it's doing it in columns rather than... It's whatever... The thing is as well, it's quite like agnostic. You can give it any sort of like thing to optimize, and it will optimize that. So if you're like, I want columns that are the same, it'll do that. If you want groups that are the same, it'll do that. You can define anything, and it will try and optimize it. So how does the simulated anneal thing and the synth fit together? Let's get caught up here. Not even there. Oh yeah, that's boring. So a single input, which is my control knob, goes into the multi-dimensional map, the single to many mapping. It changes the parameters. Some sound is made by the synth. I measure the perceptual loudness. I could have chosen another descriptor. I might have done the energy or the RMS or any number of things. I just at the time chose perceptual loudness. Probably a combination of naivety as well as convenience. It looks at whether the parameter that it's chosen as a single input has increased or maximized the function, and then keeps moving through iterations. Now my optimization function that I chose was I wanted it to always reduce in amplitude. Because I found that the edges or the corners of the parameter space were more interesting when it was very, very fragile and fluxing quite a lot. So I have it maximizing the dBs, but I've inverted the scale. So instead of going from 0 to negative infinity, it just goes 0 to positive infinity, and it maximizes that. The thing that you don't see as well in a lot of the demonstrations is the bad moves are not shown. They're just concealed so that you only see like positive progress. But in the way that I used it, I kept all the bad moves as like a musical voicing, I suppose is a way of putting it. So I think now is the time to hear some sound. So to sort of prime you, this is one thing that came out of the system which I chose to be the primary thing that I would like to show you. However, there's multiple versions that I've done with the system. And we can listen to some of those in a bit. But yeah, we'll just listen to this one in full from start to finish. I'm just going to start with it quite low in case. So these are the things that I was thinking after I'd gone through this process of building the system and actually making some sound with it. I'd reached a stage where I was sort of behaving as a sort of meta composer, and not right, I guess where I wanted to be, where I was actually just tweaking parameters as a form of composition. So like we did with the cat reassembler. That needs context. I was basically working with these kind of simple parameters, so the cooling rate, the starting temperature, as well as this kind of learning rate, which dictated how random the moves could be in relevance to the temperature. So not only was it becoming more strict in accepting bad moves, it was moving less far in the parameter space as the temperature moved down. And there's quite a lot of modifications to the algorithm that people have done themselves, where like they do other stuff, like they only keep good moves in a memory, and they only move between the possible good moves and unknown moves. So there's all, that was just kind of my way of controlling the algorithm and giving it trajectory. Yeah,
I have a question about the sound, like the piece that we heard before.
Yeah.
About the stepping that we hear.
Yeah, okay.
Like, is that something?
The clock.
Yeah, is that something you want? And that's the iterations, for example, on the
that is the iterations.
So we hear them. I mean, is that something you want to be heard, or?
Yeah, I mean, like it's something that's imposed on the piece through the technical part of it. And this is kind of what I was talking about earlier with, you have like the compositional thread and the technical thread. And at some point I was like, that's what the technical thing does. And I was like, and that's what it's going to be. And I'm not going to like try and code an external to fix that. Like you start getting deeper and deeper into that problem. Although now with using some of Alex's FrameLib, like I'm making an audio rate version, which is all smooth. And each iteration, it like measures the change over time. And like you can get rid of a lot of those sort of idiosyncrasies by overhauling it.
So you can get to smaller steps.
Yeah, I mean those steps are 30 milliseconds. And they kind of just sound like 64th notes or something like that. But to me, as well, this is another thing. I heard it so many times that starts to dissolve for me, and I just stop hearing that. Yeah.
Some kind of early versions of the piece that sound quite different.
Are you asking for the bad ones? Is that what this is?
Not necessarily the bad ones, but you have some ones where we get this kind of like motorbike kind of
I've got motorbike one.
Yeah.
Yeah. Do you want to hear the motorbike one? Okay. All right. So this is the motorbike one. So I'll skip 4 minutes into the future. Oh, that's quite good actually. It's 2 minutes. So it's quite like homogeneous across the whole duration, and it does explore the parameters, but perhaps like I got the parameters wrong, or perhaps it was not extreme enough because it stays in quite a narrow sort of dual space. But I have some more ones that are quite interesting to show. What I liked about the whole process was that I didn't have to work in detail too much once I'd made the system and done like kind of nitty-gritty technical things, and I could think quite generally about everything. But that's something that's actually exhibited across both, or like almost all of the iterations, or the things that came out of it, is this kind of duality between noise and pitch. And so with the motorbike iteration, there is some separation. There's kind of this sparkly thing that happens at the top, and then the bass thing that happens. And sometimes they come apart from each other, but most of the time they're stuck. Whereas in the iteration or the version that I showed you, like I quite like the separation that happens, and the two streams actually become their own thing, which was actually something that I didn't encode. It was just, and that's what I like about this whole making decisions process, was that things came out which I didn't specifically plan, but perhaps are inherent or accidentally there. Let's do a little breakdown. So around the 1 minute mark, there's this sort of divergence from the pitch noise thing that's set out from the beginning. So if we have this kind of setup and this exhibition of ideas, they start to pull apart and start to be clawed apart. Both kind of like sonically they're more defined, but temporally they're quite a lot longer when they're presented as well. There's this idea that came about, or there's this behavior that came about where the pitch and the noise start to develop. So at the start, it's quite erratic. I guess you can hear the stepping movement between pitches, but they actually they start to become a lot smoother. So if we'll just get some pitch here. Compared to, so as well with the noise, it becomes quite narrow band compared to quite broad band. So a lot of that kind of sound, as well as the end, which is getting smaller and smaller and quieter and quieter. As well, this thing. So I talked at the start about having some sort of relevance or sectionality to the work that I didn't have to impose or directly implement. There's quite a lot of borrowing that occurs. So so like at the start, not at the start, about 20 seconds in. So here we have this quite low grumbly idea, which is only returns once. It's recapitulated audio. These are byproducts of the algorithm doing its thing. It gives some sort of intentionality to the behavior, as well as some sort of structural importance to those moments because they happen again, which is quite a simple thing that composers do, but to get there from quite a complicated and roundabout way is very satisfying. So where am I on here? Yeah, so the things that were frustrating about this was my inability, or perhaps my own, I wouldn't say like puritanical view or anything, but I didn't want to intervene with the algorithm too much while it was running. I didn't want to be sort of improvising with it or stopping it from doing its thing. So there's this frustration between myself and it when it's like doing something great and then it stops doing it, and it's like, why? How dare you? I made you. Why won't you just keep doing that thing? But at the same time, I'm trying to retain that sort of level of abstraction from the machine, and to let it do its thing and see what emerges.